undergraduate studies in physics at College, which is in Iowa, or you're on the Iowa side, or Illinois side? Or?
Yeah, we move back and forth.
Okay.
I claim it all as home, you know.
Okay. He got his PhD in materials science at Penn State University. And I want to note under the direction of John Morrow, who himself got his bachelor and PhD here at AU. Some of you know him. Collin joined us here at AU last fall and already has been making the news with the work incorporating waste glass and concrete. And that's what we'll hear about today, right? So
Great.
All right, all yours. Let me fix this. Here.
Perfect. Thank you so much for having me. That's exactly right. So today I'm going to tell you this. I'm going to take credit for, but I'm largely done by my students. I'll try to hold them out as appropriate as we go through now. The last thing I need to say is please go ahead and stop me, raise your hand. I'd love to answer questions as we go through. I understand that there's a process. I'm okay with that. With that being said, let's go ahead and get started. Oh, and it works. Oh, almost works. Great. So my research group, many of my students are here today. We're split amongst two sides. So half of us are working on the physics of glasses and a little bit of physics of ceramics. And on the other side, we're really focused on sustainability. These may seem disconnected at first, but ultimately the problems that we face in sustainability are chemical and physical problems intimately related to chemistry and physics. I want to see how well this thing keeps up. Great. So when we talk about the sustainability of glass, what are we actually talking about? There are three different aspects of this. The first is the production of glass. Glass is responsible for about 0.5% of carbon emissions in the US. So 1/200 of our CO2 molecules we're putting into the air is coming from glass manufacturing. This is expected to grow in up to 2% by 2035 because we have more and more glass that is required for our renewable applications. If we think about it, if we imagine a solar panel, 5 wood, the majority is glass. We think about wind turbines, those blades are fiber blades. So as we're talking about carbon emissions, part of this is as we scale up our renewable energy infrastructure, we'll also see a scale of carbon emissions related to manufacturing plants. Another part is actually recycling. How can we use recycling to cut down the overall lifetime carbon emissions? There's also new glass applications, new kinds of glasses that are being created for energy applications. These include the hydrogen fuel cells. So, for instance, a glass can serve as an intermediate of a hydrogen fuel cell. It's being developed for hydrogen-driven aircraft. We're not going to focus on that so much. Today, we're going to talk a lot about production, and we're going to talk a lot about recycling. So, of course, this, 3 R's, and I'm using this popular. There's, of course, new approaches, but today we're going to bring kids in 3 R's. Let's see if that's good. If you'd like to argue with me afterwards, I'd welcome that. So when we think about these 3 R's, when we're talking about reuse, reduce, recycle, we're not just talking about bottles, right? We're not just talking about things that are most often associated with glass recycling. Glass shows up in all sorts of everyday applications. When we think about windmill blades, right? The fiber in the windmill blades is glass, specially designed glass with high gum sponges to be able to reach the demands, not bend. Solar panels, by mass, like I said, are mostly glass. And it's a specific kind of glass called low iron glass. For reasons we'll get into, this is one of the most carbon-intensive glasses to produce. Of course, we have our different bottles. And of course, we have to have different recycling streams for different kinds of bottles because their chemistry is different. Of course, we have our traditional glass, right, that we see in the videos, probably the most common application of glass that we're talking about. But also, glass is part of technology, right? And here, your laptop screen is glass made by Corning, most likely. The iPhone screen Or your tablet screen is also a glass made by Corning or Schott or AGC, depending on what kind of equipment it is. AGC being the Japanese glass company. Your Samsung glass or your VR glasses, your VR goggles. Inside of them, they contain high quality optical glass, usually produced by Schott or other small companies, where we can use the glass for our optical applications. Right? The same kind of glass that we're using in telescopes, the same kind of glass we're using in microscopes. We also have the same kind of optical glass inside of cameras. And, you know, this might seem unintuitive at first, but the next generation of data storage has been proposed in silica discs, where you can write way more information than any of the traditional uses of glass. Lastly, the next generation of microchips are being built on glass. And that's because glass allows you to build microchips on either side, on both sides. So there's this pioneering work towards glass manufacturing of microchips. So in all of these devices, it is possible that they either contain glass or they soon will contain glass. This demand for glass, right? And what I say by glass is a wide kind of arching description. What I really mean is materials where the atoms are not ordered. Materials where the atom ordering the atoms. And all of these applications are only going to grow, right? We're not going to reduce any of our applications. So we have to really consider, how are we going to decarbonize this industry? So I've broken this talk into 3 sections. We're going to start with reduce, and then we'll move to recycle, and then we'll move to reuse. Like I said, I'm going to mention the work stand. So under each section, I have my students who did the associated work, or are undergoing the associated work. In this case, Vasily started our work on reduce, and Montana is continuing our work on reduce. Any questions? River, have I lost you yet? Right. Well, okay. Reducing the overall amount of glass is not good, right? That's not actually what we care. What we care about is reducing the amount of embodied carbon that goes through the land. In other words, just because we're producing more glass does not mean that we're necessarily producing more carbon. The goal is to produce the least amount of carbon per pound of glass, and then to make sure that at least little of that glass is left. Those are the things. Reducing glass overall is not necessarily a great idea. You know, there's good reasons to avoid reducing glass. And there are many solutions out there that do reduce the glass at the cost of other options, right? People often argue that maybe less glass would be more plastic, right? Or there's this company in Italy that I won't mention. They make very thin glass bottles. And then we do a very carbon-intensive process to make sure that those bottles are very strong. Right? So they are reducing the amount of glass, but they're doing it at the cost of another carbon emission. So what we're really looking for overall is how do we reduce the amount of carbon emissions per thing that goes into a land? That's what we're doing. Right? And there's 2 contributors to the actual carbon emissions of glass. The first is the raw materials. And the second is the actual process of that. So first, if we think about our raw materials, for the most common kind of glass, it is soda lime. Most bottles, most windows are what we call soda lime. Soda lime silica. You have soda, lime, silica. Don't you love it when it says it, right? So this is actually a sodium mine owned by a Turkish company in Wyoming, where they're digging up sodium carbon. This next section, anybody know what this is? Do you have geologists? Oh, no geologists. I can say whatever I want. It's great. This is limestone. So this is calcium carbon. And then last up, we have silica. Silica sand. Right? Overall, these 3 things together, when melted together, will form a very nice glass. We also, however, often include color. Color is a name for a process recycled sized glass. So AKA, we get some waste glass from the consumers, we process it, we clean it, we size it down, and we put that back into our glass. The reason glass manufacturers want color back into the melting procedure is because for every 10% of color you use, you cut your emissions to 3 to 5%. This is a big energy savings. In the US, it's common that we melt with about 30% color. In Europe, in Germany, they'll reach 70 to 80%. But even though it provides cost savings, the defects that are in your color, the issues, the chemistries, the impurities end up in the final glass. So part of your ability to be able to do this is based on how clean your glass is actually getting. These two are particularly challenging. The sodium carbonate and the limestone, calcium carbonate. They're carbonates, which means that they are what we want with sodium oxide tied to a CO2 bond. So when we melt it, that extra thermal energy makes the CO2 run away. So that CO2 is being released directly into the air. And this is part of the responsibilities of carbon emission. Same with the calcium carbonate. CaCO3, CO2 leaves, and that CaO. So these two are already responsible for a significant amount of carbon emissions. Then we go into the process. I stole this from a colleague of mine. It's a great drawing. I love it. So how does this process actually work? What happens? Here. Nice. All right. Love it. Okay. So Sarah, this is your hot. So this is where your raw materials are being fed into your tank. And what we have is we have a tank that has a different temperature on top as it does in the bottom. So it self-stirs. It's creating a flow pattern. And so the materials come in on top, they start floating around, and then there's some dwell that it takes for it to go through the neck or the waist, which is right here. On top, the traditional way of manufacturing is that we burn natural gas. So we burn natural gas. For an example, up the road at Auburn, New York, is Guardian Glass. Guardian Glass is owned by Coke Industries, and it was part of the vertical integration associated with the Coke products. And they decided to do this because a large part of making glass is the energy that goes into it. So it's a natural thing. Even though they discount gas, they still spend about $1 million a month on the natural gas to get it used. Not a small amount. So your particles come into your mouth, they circulate around, and as they circulate, they slowly dissolve. This tank is what's called a continuous furnace. We never empty this. As soon as this furnace is turned on, you want to run it for all the time you can. Usually between 7 and 12 hours. 7 is bad. So we try to get it as long as you can. A typical tank will cost between $10 to $40 million. So you want to keep this operational as long as possible. So over here, this is the direct primary melting zone. You go through the waist or the neck. You have a little bit more circulation to help get rid of the bubbles. And then you're actually drawing it out. And this is where you take the hot block, the glass, and you make a bottle or a flat piece of glass, whatever you're choosing. Make sense? Awesome. Oh no, the clicker's slow. Oh, there we go. So as we go through this, I want to keep a few things in mind. The current manufacturers of sodium silicate, this is the commodity. Most manufacturers are making around a cent a pound. It's not much. Your profit also does not come from just being able to deliver a pound of glass directly. It's dependent on your ability to shape it, turn it into something that's useful. So this is a slim margin industry. It's a slim margin industry that constantly and decisively needs to be decarbonized. The energy costs are amongst their highest expense. Sorry, not their highest expense, amongst their highest expense. Energy costs and raw materials together are part of the highest expense. It takes 2,500 kilojoules to melt 1 kilogram of this. That's a significant amount of energy. So the energy is a large part of the section. one of the few ways that we've been able to actually make money as a glass industry is by getting to bigger and bigger factories. We look 40 years ago, typical tank was around 200 tons a day. The largest tank in the world just came online that does 700 tons of glass a day. So part of this, they are only able to continue to make their profit as the cost of glass is significantly dropped by making larger and larger products. The cost of a bottle today is significantly less than it was in the 80s and 90s. Environmental regulations are a big part of this. There are a lot of environmental regulations that, in my opinion, are being made without exception for what it actually means. So what's happening is that you're not actually seeing a benefit. For instance, the European glass industry is trying to meet their demands, but they can't. So a lot of their European factories are moving to other countries outside of their country where they don't have to obey any carbon emissions. So as a result, a lot of these carbon emissions standards are not actually having moving which country is actually emitting the carbon. And then glass is infinitely recyclable in theory. It's important to know that companies want glass, it reduces their energy costs. The basic glass gets clean, size, and ready to use. And that process, taking waste glass and processing it into something that's actually usable, is not trivial. Okay, so there's a couple different ways to melt glass in today's age. The most common is this fuel-based furnace. And what you have is you have a cross-fire beam. It's going over your melt. The idea is you fire natural gas this way for about 15, 20 minutes, and you fire natural gas this way for about 15 minutes. And the idea is that creates the hottest, the top is hotter than the bottom, and that creates convection. Nice. Gotta check out physicists, right? Alternatively, there's what's this called electric furnace. There's very few of these actually. There's a couple challenges. In fact, one of the challenges is that every glass manufacturer switched to electric furnaces today. The US there is not enough electricity on the grid to be able to meet the demand for just glass. That's a challenge, right? The other thing is the glass, you have to be able to have enough current when you do it, meaning that they have to be small. So you're not doing even 100 tons a day in most electric furnaces. You're doing less than that. And the cost of electricity is a big deal, right? If you're in a place like the US where the cost of electricity is high, it doesn't make a strong economic case. A lot of the people who are doing electric furnaces, which are called cold crown melters, electric cold crown melters, called cold crown because you heat the bottom of electricity and the top is cold. Time, as we've got the main steam down, right? So in the cold crown melters, you face a significant amount of challenges. The size of the thing, where these are most commonly getting used are small specialties. For instance, Schott. Schott is a German company, partners a lot with Zeiss. You have like fancy glass, you have an Duran lab here. A lot of that is looked in electric furnaces. That's because their profit margin is a lot more than a few cents for the specialty glass that they're used to. So Schott has the energy and the ability to actually move towards these things because they're only doing small amounts. For somebody like Guardian, who's trying to do 400 tons a day, this is not an option, not yet. One alternative is hydrogen. Hydrogen has a function of this. There's always somebody, someone, who's in love with hydrogen as a solution. Hydrogen has a lot of really great things about it, but it comes at some severe challenges. One of these challenges is that you're going to end up with more water in your glass. So this is a little model that we've done. My student Vasily worked on this. And the idea was we wanted to understand what was the effect of water on the actual fracture of the material. So, okay, how does water make this material weaker or stronger? Good? You on board? Any questions so far? No? Love to hear. Okay, great. So, we're in great shape. So what we did was we wanted to do some modeling. So what we did was we fixed the amount of silica, so the amount of sand we're putting in, and then we changed the ratio of how much water we're putting in versus how much sodium we're putting in. And we changed the amount of sodium we're putting in from more water or less water and more sodium. And we really wanted to understand what was happening. So these are simulations called molecular dynamics simulations. Blue is hydrogen and red is sodium. We then made a big slab in simulation with individual atoms, and we pulled them, right? So we can see how much force it's taken to open these things up. And so we can watch the simulation. And so what you can see is we're deforming it in the x-axis, and we're seeing the crack slowly get larger. So of course, and then on the right, we see the corresponding surface. One more time, just for, the simulation took a lot of work, so we want to show it off as often as possible. Great. So now we're able to look at the actual effects of the stress propagation on the. So we're trying to understand how the fracking behavior change in the presence of water. And what we found over here, this was the important part, is that what we found was that the water was changing the way in which the crack happens. So it wasn't necessarily, so it changed it so that the crack would prefer to go through scent with water. So the crack is finding its way to places water is. And so that means that it's offering new routes for the crack to propagate, and as a effect, lowering our fraction. So the conclusion from this part, what I'd like you to take away, is that there is no melting technology. So there's still a lot of work that it's going to take to be able to get either cold ground or in our case, hydrogen melting off the ground. We're predicting that hydrogen melting is going to severely affect the strength of our glass. And thus, there's new solutions that are required to be able to explore that. New solutions that are going to come up with to be able to either melt the hydrogen or keeping the water out of our glass, or melt some other alternative gas that clean and combust and won't leave residuals inside our glass. Next, we move on to recycling. Before I move on to recycling, any questions? Great. So recycling, this work was pioneered by my student Denise. There she is. Basically. And so this work is her excellent work that I'm really excited to show you. And the follow-up work from that is from my student Ian. So today we're going to be telling you a little bit about how we're understanding recycling and the problems associated. So glass recycling is a problem. In the US, we have a much lower recycling rate. About a third of the glass gets recycled, as compared to Europe, where in some countries they're exceeding 80%. So how do we understand this, right? How do we actually work through this recycling problem to be able to understand what are the limitations, what are the factors? If you go out and speak to the MRF operators, municipal recycling facilities, MRFs, they'll tell you all sorts of things. They'll say, it's the American consumer. The American consumer just doesn't care. Or they'll tell you the distances are just too big, too far, can't do it. Or they'll say, the way that we distribute glass has no hope of ever being reversed to collect the glass. They say all sorts of things, right? It's the government's fault, it's the company's fault, it's the consumer's fault. Those are the three places that we generally place it. Who's that? Not really about this question, though. If you ever meet with a different person, I want to talk about that. Today we want to answer who can fix it. Who can actually do something about it? Because it doesn't really matter whose fault it is. So one problem is this distance. They're right. If we compare the size of the US to Europe, it's a significant problem, especially if you're generating waste glass in the middle. where everything's into a recycling facility. I'm from Iowa, so I can talk about being in Iowa, but what is the role of science and technology in this solution? These are all things that we really care about. There's of course quite a bit of preliminary work out there based on modeling waste. You can look up this really nice website, but again, I won't take credit for. Denise found this really great website that explains the different pathways and has basic models built in, but models for general things, not models specifically for understanding glass. Glass is a little bit of a different supply chain than a lot of other waste. So in general, what is the lifetime of the glass? You go and you buy a Yingling, a Coke bottle at your favorite restaurant, right? What happens to that Coke? Well, the amount of glass is proportional to the population density. Usually, of course, there are a few touristy areas that can use more than the actual people who live there. Then once you have that, you can put it in a recycling bin. A large portion of the glass is recycled, then goes to landfill. Or, if it's really doing a great job at recycling, what they do is they move it to a material recovery facility. The material recovery facility then tries to sort, tries to extract that color that the manufacturers want to get. There's a new trend where the municipal recovery facilities are not doing it themselves. Now there's secondary operators who can send that to, and they'll only take your highest quality glass and just make money on it. So there's becoming an increasingly complicated supply chain to be able to get it back. And then at the end of the day, the glass that is recycled, large portion, goes back into a furnace. That glass that goes back into a furnace helps cut the energy costs, helps make the melting more efficient, helps overall up until the point where there's so much waste glass that we're creating defects. The key here that we really want to explore is what is the cost associated with these two end of life, right? So one end of life is recycling, one end of life is landfill. And the thing that we're really curious about, and by we, again, I mean Denise, right, is the processing cost minus the value. The value is greater than the processing cost. This is a negative number. That means in our model, it's favorable. Our processing costs are greater than our value. The numbers are positive, and that is unfavorable. So we want to get this number as negative as possible and find geospatially where is the negative numbers? Why are they negative? So first thing we did was we dug up the data. And we found all of the locations where there are MRFs that say they can handle glass, given by these green triangles, the glass factories that the glass could actually go to, and the landfills that set plants. So now we have a geostation, right? This is inherent on top. So the question is, if I generate glass here, is it cheaper to send it to a landfill, or is it cheaper to recycle? Of course, landfill okay. So there's a cost to landfill, right? Which is the cost to move 1 pound of glass 1 mile times the distance to the landfill, plus what is called a tipping. Whenever you put waste into a landfill, you have to pay a price per ton to be able to put waste in. In New York, it's around $70 a ton, right? Higher? Usually. $12. Again, it means we're right. And then the cost to recycle is you have to transport it from where it's located, Z, to the recycling facility, to the MRF. But then you also have to transport it from the MRF to a glass factory. So this is the big downside of recycling, is that you can't just take it one place, you have to take it two. You have the same transportation cost, because it doesn't matter if you're taking it to a landfill or if you're taking it to a factory. Either way, it's roughly the same cost. Then you have another penalty, which is the processing. How much does it cost me to hire the labor, buy the machines and depreciation to be able to get this glass from the waste quality to high quality that I can go back into a glass furnace? But the one advantage recycling has is value. Factories ultimately pay for their goods. So unlike this other case where we're only losing money, here we might make some money back. So this value is really what's important to being able to understand the nature of this. So let's take an example. Let's say I'm here in Albany and I generate some waste flakes. I have two options. I can send it to the landfill over here, or I can send it to a recycling facility, and then that recycling facility will send it to this fiberglass. This is Owen's Corner. Are you from Bethlehem?
Yes.
Oh, nice. So this is an Owen's Corning factory. And so the idea is that you are producing this waste, you can send it here, here, and what decides ultimately in our model is which one is the lower cost. Here's a little algorithm that we use, and we evaluate this on a per zip code basis. So we look at all of the zip codes, find their geographical average, and evaluate from there. Doing it on a per street basis turned out to be really computation intensive, and doing it on a per county basis was too coarse to get any sort of reasonable results. So we got a map. So from this, we can make a prediction. Everywhere that is green, it is more favorable to recycle. Everywhere red, it is unfavorable economically to recycle. And what we can see here is that essentially between New York and the capital district, capital region, I'm not from New York. So from New York to the capital region, this is all green. And this is because in particular, there's not many landfills in New York. So the cost of shipping either way is, and the little bit of value you get for shipping it out of New York for that amount of material makes up the overall cost. Syracuse has two factories right nearby in the town, so that helps a lot. And then down here in Ithaca, you also, Ithaca, right? That's not yeah. I'm learning. So down here, you have a bottle glass factory right off of it. So in all of these factories, in all these cases, they are only being, their land is only being met through local factories, through local glass production. And you can see this, right? Wherever there's a blue, wherever there's a pink factory, we can match, right? Of course, some of this stuff we have to send to New Jersey or Philadelphia. But these things are really being driven by the local glass companies. So we can look at how much our assumptions matter to the end results. And as a result, how much these parameters matter overall. Right? So if you're, let's take this first example. If you're P minus V, meaning you're making a lot of money per pound, if you're making $1 per pound, all of the waste glass in New York is so valuable, you're never going to get it. Conversely, if you lose $1 per pound, you're never going to receive economically. It makes no sense. If you go over here for the tipping fee, right? If it takes 50 cents to be able to put your waste glass into a landfill, you're also going to reach 100% recycling. And if there was no cost to transport the glass, you also reach 100%. These things are fairly intuitive, right? There's not a huge surprise here. But what is a surprise to many is that there is no consumer behavior. Yet, we're actually matching the DEC's numbers and maps of where recycling is happening. So why is that a factor? Why is that happening? And what we found is that places where people make money, they invest more heavily in the recycling industry. The more heavily you're reminded to recycle, the more often you're reminded to recycle, of course, the more often you are going to recycle. Consumers want recycling. All of the surveys say consumers are willing to do a little bit extra to make recycling. But it's a matter of having the infrastructure for somebody to make money off of it to be able to build that infrastructure. And once our government radically changes, unfortunately, we are trapped in a society where we're not trapped in a society. We're trapped in a situation where we have to have some sort of economic driving force to be able to make these things come true. We could also look at new possibilities, right? So if we look at adding a factory, if we added a factory to any of these locations, we would see an increase in the overall recycling. The largest increase was if we put a factory somewhere between Rochester and Buffalo, which makes sense. Rochester and Buffalo, we have factories too, without sending it through customs to Canada, which doesn't happen. I can tell you, they don't like you shipping international waste to Canada. Conversely, right? Or over here, where we would add a MRF would also improve recycling. So what you can see again is that this factory in Pennsylvania right here would benefit if there was clean glass coming from the southern tier. Large amounts of clean glass, but nonetheless clean glass. In between here, it's the same issue. We've got to feed that factory in Auburn, in New York, in near Syracuse, that is the Owens, Illinois factory, OI factory. And then over here, we could feed the Owens Corning factory more if we could build enough of these facilities. So also from this model, we can make some recommendations. We can say, if we change these things, create these things, what are the biggest things we can see in the resultant? Bill, if we change these things, what will make the largest resultant effects in the model? So if we decrease the transportation costs, we can make a 1 or 2% change. But how do you decrease the transportation cost? I don't know. We can make MRFs perfectly efficient. We made that every single pound of glass that went into a MRF came out clean and beautiful and wonderful, and the right size, the right shape, everything. It would increase our recycling rate in New York State by 20%. Also, we could build a new glass factory. If we built a new glass factory near New Buffalo, we'd be able to increase the overall recycling rate to 4%. That was more feasible, but there's not more demand. The current demand for glass in New York is being met by New York and Pennsylvania factories. Increase the tipping fee. If we increase the tipping fee specifically for glass, the penalty for putting glass into a landfill, we would also see a 1 to 4% increase. And then lastly, if we increase or decrease the processing cost, the amount of cost it takes to turn 1 pound of dirty glass to 1 pound of clean glass, or increase the value of the result. There's many ways to increase the value of glass, right? You could put in regulations, you could put in subsidies to help process the glass, or you could come up with new applications for waste glass. You create new applications, you'll increase the demand, and thus you'll increase the value. So here, we really want to point out that the consumer is not the limiting factor in glass recycling. It is the inherent financial system associated with it. And that is what must be able. The only real way of doing that is coming up with a new technology that uses waste gas, or new technology that decreases the cost of processing waste gas. So in the vein of new technology, I'll move through this a little fast because I've been talking about. We've been looking at putting new glass in. Why? Concrete is a mixture of cement, water, and aggregate. What is that? Rocks. Right? That's what it is. It's the stuff you put in to fill up space. You can make concrete out of just water and cement, but that turns out to be really expensive. So you put in other things to take up space. Not as. And the other reason we want to focus on concrete is because concrete as a whole makes up 7 to 9% of the world's CO2 emissions, and have really good for their estimates. This is a huge number. And often when I say this number, people are like, well, we should cut off cement, right, worldwide. I often like to point out that this is not a solution, because the areas that use the most cement are the developing nations of the world. They're using cement and concrete to be able to build themselves infrastructure, to be able to build a better future. So cutting off concrete hurts developing nations way more than it hurts developed nations. So the only real alternative is to figure out how to cut CO2 emissions out of concrete. Foam glass is one such anomaly. Foam glass is a really old technology. Get some waste glass, you put a foam engine in it, put it in a furnace, you get a porous cinder glass. Turns out it works well enough. You can change the density, you can change the properties. Most importantly, it's cheap and increases the value of this glass. I'm going to skip this. This is a lot of chemistry and not my light. Sorry. And so what do we do? So we made some foam glass that's actually compatible with concrete. And so we've been working with two companies. SQ4D is the first company, where we've been working on actually 3D printing these foam glasses into houses. We're hoping that SQ4D will be able to print a building here on campus using this material. The other one that we're really excited about is this project we have with Savannah River and this group called Silica-X. And what we've been doing here is we've been trying to make foam glass the same way that reacts to the ocean. Right? Because there's so much porous space, we can fill it in with reactive materials, and the glass won't stand. So most concrete fails when something inside of it expands. So by giving it space to expand, we're letting it expand into negative space rather than expanding and cracking. And so we're really excited about this. This is the kind of process that we're doing, right? So we're mining these recovered materials from landfills. We're then processing these materials, we're turning them in. I don't know what I honestly don't. I come up with this process and I don't know what you care about, but the marketing people tell me to use those terms. So, you know, this is what we're here for, right? I think it's just pure, but whatever. I digress. And then we're going to be launching actual experimental test seawalls next spring, where we're going to be sinking 1 meter by 1 meter by 1 meter cubic blocks of our piece of concrete off the coast of Long Island. And we have divers on that who are going to sink like every few months to look at the evolution of the material. And all the small scale testing, we've actually been able to get really nice results. And overall, we're really excited about this process of turning this waste glass into a material that lowers the CO2 emissions of concrete, and overall offers a possibility of improving seawall retention, right? This is a really nice idea, right? Because a lot of cities are on the ocean. So we're saying, let's use your waste, let's use your byproduct to try to protect your own cities. So we're really excited about this. And then reuse. I'm gonna go through this kind of quickly. I should point out, I didn't do any of it. I literally just asked them today to see other slides. So most of this work has been done by Aaron Potter, who actually manages my lab and does the things that I should probably be doing. So not only does he do the research, but he also does all the managing the actions. So really, you know, great this. So Aaron's been working on bottle reuse along with Rebecca and Greg. Greg is from a small company that we've been working with called Vitricity. Bottle reuse, as we know, used to be really popular, right? We all remember milk being given reusable glass. And every time I bring up reuse or glass recycling, inevitably somebody of a slightly grayer hair color, then some of my students say, well, I got milk from reusable. Why don't we do that? And that's true. And it's because there were the same area of financial issues with that model. There's still some premium areas that do. But in terms of actual costs, the cost of goods coming from a farm has dropped significantly. Right? So I think Pittsburgh Dairy still does reusable milk or reusable glass milk jars. And that's great, but their cost is 2 to 3 times higher than milk from the store. So it's very different financial model. And so what we wanted to do was we wanted to look specifically at bottle use and point use. There's several examples of reuse systems working across the world, but there's really no good example of reuse working. Closest we have is Ontario, Canada. And I don't know how you know about this Canadians, but that was a joke. Yeah, I love our Canadian neighbors. So Ontario, Canada has a very effective beer bottle use. So we were looking at implementing some of the technology we already have for beer bottles for wineries here in the Beer Lakes regions. We've been going around meeting with these vineyards. It's been a very difficult task. You know, going to these vineyards, having to sample the wine, while we discuss recycling, you know, it is a responsibility that we are willing to take on, just for you, right? And we were also doing polls, right? We found that there's actually a lot of mixed feelings about bottle use amongst the vineyards. They are not straightforward. It's not that everybody wants to do reuse or everybody's against reuse. As a matter of fact, in our experience, most people want it after we cross off 5 or 6 asterisks. But the asterisks are really important. For instance, I'm going to move through this. There's a lot of concern about health concerns. Are they really clean? You steal Aaron's analogy. Stole his work, might as well steal his analogy. After you clean a bottle of pickles, take a pickle jar, you open it up, and how many times you put it through the dishwasher, it smells like pickles, right? Not a lot of people do get the pickle smell out of the pickle jar. With wine, people really care about it, right? If they open up a new bottle, or a bottle they're about to fill, it can't smell like another one. These are real concerns. So we included a financial estimate. Here we go. So we wanted to actually investigate the service of these bottles. We wanted to understand how is the service of the bottle changing? Is wine being like that? What is it happening? And so what we actually found is that over time, you actually see much higher water content stuck inside the structure of the glass. And so what's happening over time is that the wine is actually changing the surfaces of the glass. And so reuse is not so simple as to just directly reuse or to just wash. You have to actually scrape out the new surface, whether that be chemically or whether that be done physically. And you can see this was a really to do this project. We had to go get wines of a bunch of different ages. And then those wines magically emptied themselves. And then we got to do science on bottles crossing 9 years or so. So then we got actually measured and we found a classic diffusion loop across the deck. And so this tells you, you know, after 4 years, you've changed almost a fifth of a micron, sixth of a micron. So it's not so trivial. There's actual real measurable changes happening in the surfaces of bottles as one considered that you have to when you're considering reuse. And also, can you make a business of it, right? As we were saying, we're looking at financial incentives, realities, and it turns out you actually need a significant reuse return, fraction of the bottles being reused for you to be able to actually make money, for it to be actually financially feasible. Much higher than any rate reported anywhere in So reuse is on its way. It's a challenge, and we're definitely going to need other financial structures to be able to investigate and figure out whether it's true solution. With that, thank you so much. I want to talk. Thank you.
I have one more your call. Can you go back to the glass section, the very last slide of the glass section?
Which glass section?
The first section.
Yeah.
Before you got into
The recycling section. This one.
So Am I not seeing it, but what if there was a line there, action, that was to incorporate the environmental cost of production and importation in terms of CO2, right? In terms of carbon emissions. You would have an increased cost of production and increased cost of transportation. It would lead to different efficiency figure and could be reordering.
Yeah, so that's a great question. So just to repeat that a little bit, sorry, I'm supposed to be over here. Just to repeat that, I believe the question is, why isn't there a requirement for them to pay for their end of life and transportation costs of glass? Exactly. So the carbon tax works really well overall if it's countrywide. But the problem is these furnaces, it may work for a while, right? These furnaces have lifetimes 8 to 12 years. You're not going to move a furnace. But as soon as you reach the end of that lifetime of a furnace, there's almost no difference in cost between building one in New York and building one in North Carolina. And that's a lot of what we've seen, is that a lot of companies have moved to the South to build their new furnaces because there's less environmental pressure. Also, you know, there's this real question of who should bear the cost of recycling. Is it the consumer? The consumer says, I already pay for a roadside pickup. I already pay taxes. I already pay local taxes for somebody to say they're doing recycling, and I pay for the product in the first place. Why should it be me? Government says, you know, we already incentivize this. We already put a significant amount of money towards making recycling work in New York State. It's not politically expedient. There's not a political driving force for it. Why would we do more? Companies say, I only make a few cents. I'm already financially hurting. I already pay for that. I already have to pay carbon taxes. Or some places I have to pay carbon taxes, but I already pay for the gas. I already pay all the taxes I can. And a lot of these companies are really large, so they pay a significant amount of taxes. And they say, I'm producing the best bottle I can at the cheapest price to meet the demand that's here. If you expect me to fix the recycling problem on top of it or pay for the recycling problem, I won't be profitable in this area and I'll move out. And it's really interesting the fact that companies move glass factories on the order in the lifetime of their furnaces. So for instance, now, because Mexico is having new environmental regulations, companies that were once in the US that moved to Mexico are now moving back to the US because the South has less environmental regulations than Mexico does. So they are highly mobile. Yeah, it's really sad. Like it's a real shame what happened there. And yeah, anyway.
Well, thank you.